In this lecture, we're going to carry on with the topics we have learned with the lecture on SQL. But we're going to be bringing SQL into the world of Python. And while one place Python and SQL connect is in pandas, since we can use pandas to issue queries to a SQL database, there's another major intersection in the world of web development. And the connection there is with a tool called Object Relation Management. So often in web development, when we're doing web development in Python, using a framework like Flask or Django, we'll be working with various objects, Python objects, with methods and attributes. But any object is going to be stored in memory. And so it's often useful to have some kind of mapping between Python objects that we define and records or relations in a SQL database, which we'll actually use to store our information for our application long term. There's other advantages to this kind of mapping between objects and relations. So many companies store data in SQL databases, and frequently there will be some set of regular operations that an analyst may need to do on the database. For example, you might need to filter out certain users that actually aren't real users or real customers of your company, but rather are just test customers to make sure that all the fields of your data collection procedures are working correctly. And you'll want to filter these people out whenever you do some analysis. Unfortunately, there's not really a lot of portability to SQL code. SQL is kind of an interactive ad hoc language, and there's not it's not very modular. It doesn't have nice things like namespaces to package up functionality into functions or classes. Basically, it doesn't have the features of a fully fledged programming language that make fully fledged programming languages well organized and capable of building up many layers of complexity while remaining readable and understandable. Therefore, another purpose of what we'll show you today is that it can be useful to express complex operations in Python, which is very readable and very organized compared to SQL. But then have those complex functionalities actually correspond with operations in SQL. So we're going to build up an example over the course of this notebook of some classes and objects that interact with each other, and store some information that we could conceivably want if we were some kind of company managing employees. And these various classes will later map into SQL tables and operations. But for now, we'll start with the Python view. So, like I mentioned, we're going to build some classes that represent people at a company. And the very first class we're going to define is just person, which will be the most kind of general class we'll want to reference. So a person is going to have a name, age, degree, and salary. And also have this describe method that prints out a nicely formatted sentence describing the person. And we could make person objects, Dylan, 27, PhD, physics, 90,000. So here we have a person object. We can see that. And it has a describe method that'll print out a nice sentence describing me. Now, here I just have a string PhD physics, but a degree is sort of a somewhat complicated object, right? I could have chosen to write here physics PhD or physics doctorate, and all these strings would be just unstructured text. They're not going to be easy to compare depending on how the information got entered. So we're going to give more structure to this degree attribute in two ways. First of all, we're going to define a degree class which has a level and an area. So level referring to like bachelor's, master's, PhD, area being something like physics or biology or communication or studio arts, any number of disciplines. And then the other way we're going to introduce more structure is by introducing what's called validation. So notice that person inherits from object, object being the kind of universal base class in Python. If you don't inherit from anything, you inherit from object. But degree inherits from validate, and we've defined this validate class that has a validate method that accepts some element and a list of allowed values. And if the element is not allowed, then we return a value error. So this validation class is what's called we're going to use this as what's called a mix-in. The idea is that the principal functionality of degree is, coming from its own class definition, but we're mixing in some functionality from another class, validate. And the thing we're mixing in is this validate method. And the way we use that is within degree, we have some allowed levels. Bachelor's, master's, PhD. And we validate whatever level is supplied for the degree object against these allowed levels. So now, if I tried to make a degree object that said like physics PhD, that wouldn't work. First of all, because I need to supply a level and an area. So now, I have my level, PhD, and my area, physics. But now I get a value error. PhD is not allowed for class main degree. And that's because PhD with this capitalization is not in the allowed levels. So something I might do here is just add some lower to all these strings in case people were putting in different types of capitalization for these levels and areas. And now it works. PhD in physics. So the validation is going to make sure that we only allow certain entries, certain allowed entries for these fields. And this is tends to be really important for applications, because usually, just like when we first started learning about Python, we ran into trouble rather quickly because we might write a function that expects a certain input, a certain type of input, and then a user uses that function in a way that we don't expect. So for applications that might be used by hundreds of, or thousands or millions of users, only allowing certain inputs can be very important to make sure that the application functions uniformly and correctly for everyone. So we're going to do a similar thing with salary. So I represented my annual salary here, but not everyone has an annual salary. Some people are paid weekly or hourly. So we impose more structure on the salary in the same way we did degree. We're going to define a salary object, which has an amount and a pay period. And we're also going to validate the pay period, just like we validated the level of degrees. And I'll do lower on these as well. Whoops. So now we might make a person that, instead of having these unstructured strings or numbers that don't really contain adequate information to interpret, we have now these objects that accept other objects as arguments. So Eric is 25 years old, holds a master's in physics, with a salary of $5,200 a year. And we see this string came from the degree and salary repr methods. Degree returns, holds a master's in physics, master's in physics. And then salary returns the formatted number per year calculated from the amount and the pay period. So we're gradually building up complexity here, but still this is fairly simple. We have just a couple of classes. These would maybe correspond with several different tables in SQL. So I might have a table of people, a table of degrees, and a table of salaries. This way, if someone has, I might have like 100,000 people, but only a few hundred types of degrees. So rather than replicate over and over again the different types of degrees, I might have a degree table that gives them some kind of ID for each one, and each person just has like a degree ID or something. And that way, rather than having many duplicate degrees in the tens of thousands or hundreds of thousands of people, I can have just a few hundred degrees. So let's continue and see where some of the elements I described earlier come in. So we're now going to define an employee. An employee is a person who additionally has an ID and a level of production. We're also going to define a manager who is an employee that has a capacity. So production is like the amount an employee can produce in terms of work. Capacity here describes how many people a manager can manage. And so a manager also has a method, can manage, that checks that some number n, which is received as an argument, is less than or equal to that manager's capacity. So if the manager has n employees under them, is that within their capacity? These lines, which I didn't describe, and I can't remember if they appeared in previous lectures, are just saying that the initialization method for employee is going to be the same as the initialization method of the superclass of employee, which is person. So it's going to be person init with all the arguments for initializing a person, plus these extra attributes. So this is a common pattern within class definitions where you'll see the class that inherits from some other class, its initialization method draws on the initialization method of the superclass. And that happens also for manager, where we initialize all of the attributes of an employee using the superclass of manager, which is employee. Now that we have employees and managers, we'll define some structures, some company structures, like teams. But before we define a team, we're going to define a group, which is team will inherit from group. So a group has members, and it has operations for adding and removing members, as well as finding out who the members are. So we can add members, where we simply add a member to the dictionary of members. So the key for that dictionary is the member's ID, and the value is the member object. This will be an employee or a person. We can remove a member from the members dictionary, and we can get member IDs. So we return excuse me, the keys of the members dictionary. We can extend this class by defining a team, which will inherit from group. A team, in addition to having the members attribute, which is initialized using the superclass of teams initialization method, so using group.init, a team has a name, an ID, a description, and a manager. So we, in addition to the methods of a group for adding and removing members, have methods for adding and removing a manager. We also have other methods for kind of inspecting a team. We can find out the cumulative production of a team by calculating the sum of the production of all its members. We can also check its health. Is there anything wrong with this team, or should it be functioning normally? So, for example, if a team has no manager, but it has some number of members, meaning like there are employees on the team but no manager, we'll return false. The team is not healthy. There are no managers. There's no manager for the employees. If, on the other hand, there is a manager, we check if that manager can manage the employees on the team. So, from the members of this team, we select the manager. So this manager attribute is actually just an ID. It's not a manager object. And we check that manager can manage the employees. If it can manage, we return true. The group is healthy, or the team is healthy. If not, then there are too many employees for the manager, and the team is not healthy. And if the team is empty and there's no manager, then we just return true, because an empty team is always healthy. So now we're starting to see some of these kind of like more complex operations that I mentioned at the beginning of the lecture emerge. If we had SQL tables for
people, degrees, salaries, employees, managers, groups, teams, finally teams, and we wanted to check the health of a particular team, then defining all the logic necessary for that SQL query would involve several case when statements, and it would be rather difficult to write out, easily understandable, readable SQL code for that query. But even more importantly, you would have to read the code to understand what it did. There's no way to assign an interpretable name for packaging up that query into some kind of function. So, taking a team and checking its health is very expressive. It's very clear what you're trying to do when you call this check health method because of its name. So what we would like to do, since we want to use SQL in the back end for managing the persistent data storage of an application, but we would like all the benefits of this kind of naming for complex operations. We define these classes in Python, and then we use some Python modules to manage the mapping between these classes and SQL. And that's the object relation management. And we'll come to that soon. But I wanted to highlight, now that we see like one of these complicated functions that would be awful as a SQL query, we can just package that up into the name check health. So building up still one more level of complexity, we're going to have a company, which is another type of group. But a company is going to not only have a company is a group of teams. So nowhere is that really enforced other than Oh yes, when I add members, the members I'm going to be adding are teams, of course. But that's not enforced anywhere. And I could also add individual employees or individual managers to the company as well. And so when I do production on company, and I say I.production for I in self.members.values, the members might include teams, which have a production method. It might include employees, which have a production attribute, or managers, which also, since they inherit from employee, also have a production attribute. And I think, just to make this actually work correctly, so in the example, I only Yeah. This is going to be a problem. Okay, I'm going to leave this alone for now. So in this case, so actually if I wanted this production to work, including when I have employees or managers who aren't parts of teams, I would need to modify the code a little bit. I'm not going to do that right now because in fact I only have teams as members of a company. But in principle, I could modify the classes so that this would work if I had I had employees or managers who weren't assigned to a team. So I also have here I have a check health method, which for each member of the company, each team, I check that that team is healthy and print out whether or not an individual team is having a problem. And additionally, I check that all my employees are assigned to only one team. And I have this helper method, single assign, to do that, where I take let's see here. So for each team and for each what I do is I return a member ID for each member on each team. So for every team I, so I'll relabel these just to make this there we go. So member ID, for each member ID in a team, for every team in the company. And then I count out the number of times each ID appears, and if any ID appears more than once, so the most common ID should appear exactly one time, basically. It shouldn't appear more than one time. And if it doesn't appear more than one time, if it does appear more than one time, then I'm going to return false here. So I build up this list of problems and I return problems. And hopefully that list is empty, but perhaps not. So we're seeing now that I can do some pretty complex things with these objects, and that they draw on the methods of other objects. So the company's check health method draws on the team's check health method. So now that we've defined all these classes that kind of build on top of each other, let's instantiate some objects and actually put together an example. So we'll have some we'll have a low salary, a mid salary, and a high salary. And we'll have some degrees. And then we'll make some employees. And some of them earn low salaries, some of them earn mid salaries, and they have different degrees. And then we also have some managers with different salaries and degrees as well. And we have 3 teams: tech, sales, and executive. Now, Fred, Amy, and Carrie are going to be on the tech team, and they're going to be managed by Sally. Meanwhile, Erica, Jerry, Sam, and Danny are going to be on the sales team, and they're going to be managed by Arnold. And finally, the executive team only has one member, its manager, Molly. And then the company consists of the tech, sales, and executive teams. So we can describe the company. The company is healthy. It has a production of the sum of all the production of all the employees, which are these numbers. Team Tech has 4 members, producing this much. Team Sales has 5 members, producing this much. Team Executive has 1 member, producing this much. And we see here the members of the company. That's the various teams. So the first Team 1 has ID 1, name Tech. Team 2 has ID 2, name Sales. Team 3 has ID 3, name Executive. And we could even, for instance, take the company, select the tech team, pick out from the tech team member number 10, so the employee with ID 10, and that's Carrie. So, we've built these interlocking classes where when we go to actually work with the objects, it's fairly straightforward. We define a bunch of objects. We have nice expressive methods for connecting the objects. And then we have nice expressive methods for reporting on the state of these objects, or accessing their elements, their attributes. And we would like this kind of expressive handle for interacting with these objects, but rather than storing the information in memory as objects, we want to store it in a database. So here's where the object relation management or mapping comes into play. So, as I mentioned earlier, each of these classes could correspond with a different table in SQL, where each row corresponds with a single object or instance of a class. So remember, if I have an employees table, each row of that table presumably corresponds with an employee. Just like if I have an employee class, each employee object corresponds with an instance of that class. So there's a fairly straightforward mapping conceptually between SQL tables and Python, or the rows of a SQL table and Python objects. And to affect that conceptual mapping, we're going to use an ORM tool called SQL Alchemy. And this is, I'm importing here SQL Alchemy as SQL. Importing pandas as PD or NumPy as NP are extremely strong conventions. People almost always do that. This is not a conventional alias. I've just done this for my own convenience. but this is not commonplace. So we're going to work through this example once again, but now in the context of SQL alchemy. And SQL alchemy is going to handle in the background the job of creating all the tables and connections between tables necessary for us to work with Python objects with all of the actual data living in SQL. So there's going to be a lot of stuff in these class definitions, and they're going to look quite different from the class definitions we just looked at. They will have some things in common, but there will be a lot of differences. And I want to highlight several patterns. All classes inherit from base, this declarative base, which is part of SQL alchemy. This base is part of what connects the objects to SQL tables. Some of our classes will inherit from other classes. For instance, manager inherits from employee, but an employee inherits from base. So manager ultimately inherits from base. All classes will inherit from base, possibly through other classes. All classes are associated with a SQL table via a table name variable. There's no init method. Instead, attributes are declared as variables of type SQL column. So remember, Python is not strongly typed. I don't need to declare what type of variable I am instantiating in Python. SQL, on the other hand, is strongly typed. And so in order to bridge that gap, all attributes are declared as variables of type SQL column, and those SQL columns have a type, like integer or string. All attributes are typed. We use types SQL integer, SQL string. All classes contain at least one primary key. This is, I believe, not strictly necessary, but the conditions under which it's not necessary are rather complicated, and I'm not going to get into them. And relationships between classes and tables are accomplished using SQL.orm relationship and SQL.foreign-key. And I'll talk some about this. It's also rather complicated, but by looking at the example provided here and looking at the SQL alchemy documentation, you will be able to piece together how these relationships work. So there's a whole section on building relationships. So let's see how our example compares when it's run on SQL. So we're going to declare several classes. We're going to first declare classes which inherit from base. And I'm not going to have quite as many classes as we had before. I'm just going to have teams, employees, and managers. I'm not going to have And this is just to keep things relatively simple since there's already a lot going on. But I'm not going to have degrees and salaries and person and group all as separate classes. Just for the sake of simplicity, I'm only going to have 3 classes: team, employee, and manager. So team and employee are both going to inherit from base. So let's look at employee first. Employee will match up with the employees table. And it has all these attributes, all these SQL columns in that table. So it has an ID. Employees have a name, an age. And notice each of these are typed. The ID is an integer, the name is a string. The age is also an integer. And the ID is marked as the primary key because it's the unique identifier for each employee. An employee has production, salary, amount, period, a degree level, a degree area, and an employee type. An employee has a team ID, which is a SQL column of type foreign key, and the foreign key is the team's ID number. So a team has an ID number, which is the team's primary key, and this is how we're going to establish a relationship between the employees table and the teams table, which is going to do things like automatically perform joins for us. So an employee also has a team, which is a relationship between teams and employees. So each employee has some kind of like relationship or referent to the teams table. And this back populates keyword does something really cool, which is if I remove a member from a team or delete an employee, then the teams table or the employees table automatically update each other based on those changes. So changes cascade to other tables. And that would be quite we kind of like get that for free with this ORM. I'm going to skip over this polymorphic identity for now. That's going to relate to manager. And I'm going to hop over to team. So a team corresponds with the teams table. And teams have an ID, a name, and a team has members. So this is a relationship with the employees. It's going to also have this back population. And these are just stipulating that, again, when I make changes to employees or changes to teams, these changes cascade between the team and employees table. So a team has some methods. There's a manager method that will check whether any members of the team are a manager, and if so, it returns that member. If not, it returns none. It has a healthy method that checks all the things that we checked in the healthy method of a team in the past. So if there are members on the team and there's no manager, we return false. If there's a manager, we check that that manager can manage the number of employees in the team. Notice here, I have a manager method, but here I'm using self.manager as an attribute. So that's related to this hybrid property decorator, which allows me to reference methods as attributes, which is nice because all the columns are attributes. And so this allows me to use methods as if they were columns in the teams table. The interface will be the same. I can act like there is a manager column in the teams table by having this hybrid property method, manager method, where in the SQL database, I don't actually have to store a column corresponding with who the manager is. I can instead, on the fly, calculate who the manager is, but expose the exact same interface as if there was a column saying who the manager was. So this saves me storage space in my database and allows me to, on the fly, calculate kind of entries as I need them. Same for healthy. I can treat each team as if there was a column in the table saying whether or not that team is healthy. So both of these are kind of like derived fields. They depend on who is on the team. It depends on the members of the team. It doesn't depend on, or these other things don't depend on anything. Like a team has a name and an ID. Those are like independently stipulated. As the members change, I would also have to change who the manager is, whether it's healthy, what the production is. So I would have to do 3 mutations whenever I change who's on a team on the teams table. But instead, since these are calculated, derived from the members relationship, I don't have to store these in the database, and additionally, they automatically reflect the current state of information because they're derived from the members. And finally, we have managers, which inherits from employees. So managers have an ID, which is their employee ID, and a capacity. And there's this polymorphic identity thing going on, which is important for inheritance within SQL Alchemy. Basically, the idea here is there's a join that needs to happen in order to add the capacity column to employees who are managers. And I'll always be joining just to a specific set of rows in the employee table. And sometimes managers are going to be acting as employees whenever I'm like referencing these things. And sometimes they're going to be acting as managers whenever I reference their capacity. And so this polymorphic identity is in charge of handling when I'm treating an employee as an employee, and when I'm treating a manager as an employee, and when I'm treating it as a manager. And it all relates to things going on in the back end in SQL that I don't really have to worry about ever again, as long as I set this up correctly at the outset. So this is the correct way to do it, where we have an employee type that's going to say whether an employee is an employee or a manager. So employees have a polymorphic identity of employee, which corresponds with their employee type. Managers have a polymorphic identity of manager. And then managers also have a capacity, which means I can define this can manage method. Here I define this as a hybrid method, which again allows me to treat this method as a column in the table. But now it's a method because it accepts some argument other than self. So hybrid method and hybrid attribute are decorators where SQL Alchemy starts to help us. Yeah, this is basically saying what I already said. Rather than store some information in the table, which is maybe redundant with information we already have, SQL Alchemy can calculate this on the fly and treat it as an attribute. This way I can interact with objects in the same way, whether the data is stored in the underlying database or not. And the reason this can be really useful when an attribute has a complex definition is because often in database management, we will want to reference specific records by some complex definition, like which teams are healthy. And having to write this out every time we want to get healthy teams is really inconvenient. So we have two kind of options available to us in raw SQL. Either we write out this definition every time, or we store the information somehow in the database by creating a new healthy column. SQL Alchemy helps us get around that by allowing us to calculate this quote-unquote column on the fly, but act as if the information were actually stored in the database. So we're going to actually fire up a database. We're going to make a SQLite database called company.db. This echo equals true keyword is going to show us the SQL that SQL Alchemy is executing as we create Python objects corresponding with these classes. So there's some boilerplate for pushing the schema of these tables to our database. So we can see what's going on here is we're creating the tables defined in the classes that we defined above. So we have our managers table, our employees table, and our teams table. The employees table has a foreign key of corresponding with the teams table. And the managers team has a foreign key for the employees table. And then we're going to make a session, which actually is in charge of, it's an object that's in charge of translating this object relation mapping. So the session translates the mapping and pushes queries to the SQL engine. So just like before, we're going to create some like baseline objects that define kind of the salaries, the pay periods, the degrees. These are no longer Python objects, but just like basic data structures. I mean, they're still Python objects, right? Dictionaries are objects, but I am not making salary objects or degree objects anymore. So now I'm ready to start making employees and managers. So I'm going to make my employees and managers and teams just like I did before. And we see the syntax looks very similar as it did before. I have, the employee Fred, whose name is Fred. He has some production, some age. His ID is going to be filled in automatically just by enumeration. I also have this like cat dict function, which effectively just like combines the dictionaries I've defined here. And then this double star unpacks that dictionary just to show you kind of what this does. Whoops. So cat dict low salary with B business. We see this is just creating a dictionary with a bachelor's degree in business and the low salary information. And then this double star unpacks that dictionary into keyword arguments for this employee object. So I create my employees and managers, and then I can create my teams who have various members. And the members just get passed in as a list of these objects. And then once I've created all these objects, I can add them to the database by using the session. So the session will translate these teams and all their attached objects, all the managers and employees that are members of the teams, and then commit actually pushes, so this translation this add method sort of translates the object creation into SQL, and then commit actually pushes the changes to the database. So we see a bunch of insert into, and we're inserting all the employees, we see those. Inserting managers. And inserting tech, sales, and executive into teams. But the interactions with these tables appear to us as interactions with Python objects. So if I want the members of the tech team, I can ask for the members attribute. And that gives me back, it returns all these Python objects. Fred, Amy, Carrie, and employee 4. I don't know who that is, but it is a manager. It was Sally. Sally is employee 4, apparently. And we see all this SQL got executed in order to give us the tech.members attribute. And I think it's pretty remarkable that we can avoid writing all this SQL code and instead just write this very simple Python. So let's see some further examples of that. We can, for instance, iterate over the teams. For instance, if we want... we can also actually execute queries. So we can query the team table, and we can filter based on team name to get tech. And then we can say for each team returned by our query, for members in team.members print member. And here are our 4 employees again. So we have our hybrid attributes that behave like regular attributes even though they're not stored in the database. So team.members is stored in the database. We see all this SQL code being run. Production and healthy are not. They are calculated on the fly based on what's in the database. And then we can do kind of all of our usual SQL operations using the query method of our session. So all employees whose name begins with A, we'll call that A employees. And we see that's Amy and a manager, employee number 9. It's going to be Arnold. I would maybe want to modify, if it weren't too late, I would want to modify this to actually include the manager's name, not just their ID. I can also do joins and group bys and aggregations. So if I wanted the total salary paid out to each team, I can ask for the team name and the sum of employee salaries, where I join employees based on their team, and I group by team name. So the executive team is paid $100,000 a year, sales team is paid $500,000, tech team is paid $250,000. So we're a bit over time for the lecture, so I'm going to stop here. But this is a angle, a new kind of like another angle on SQL that doesn't come up all the time. It does come up particularly with applications. So for instance, the data incubator runs a website, and we have an application on our website, and interested students apply to our program, and we have all sorts of models for students, meaning like classes. So these are sometimes also called models. And the applicants interact with a bunch of other, models, like the applicants who ultimately become students. And so we store all this information in a database ultimately, but we want to be able to work with the information in the database within the framework of within our Python-based web framework. And so we do that by taking advantage of this kind of object relation mapping, which can pull information out of the database and allow us to write expressive Python code in our web framework for actually working with information from the database. So that's one example. If you search online, you can find many more examples of people using object relation management. Like I said, the major advantage is, in my opinion, that it allows you to take kind of ad hoc, not very expressive SQL queries and package them up into an expressive namespace that we're accustomed to from Python. And by doing that, it makes the code more portable and makes it more possible to collaborate and test the code base. Okay, so that concludes this lecture and the lectures on SQL. And the remaining lectures for the week, we're going to be turning our attention to machine learning. And the next lecture will be a video from Zach introducing scikit-learn.